so 10 seconds on. Okay, so let's start. Yeah, so hello everyone again. So and thanks for joining us. I'm Tomas Samoril, product marketing manager at TESCAN. And before we dive into the technical part, I just would like to highlight the partnership behind this session. TESCAN is proud to collaborate with Dragonfly Energy, an innovative US manufacturer of advanced lithium-ion battery systems. And for almost 4 years, our teams have combined SEM, FIPSEM, and Microscopy expertise with Dragonfly's R&D and production challenges to define and optimize specific analytical workflows to match various real-world battery research, development, and manufacturing needs. So today, together with Danielle, DeCapito, and Kimberly Ortega from Dragonfly Energy, we will show how advanced microscopy solutions accelerate battery development and scale up. So let's take a quick look at what we'll cover today. So I will begin with a brief introduction to TESCAN, its microscopy solutions, and main application areas. And since today's focus is on lithium-ion battery technology, I will then give a short overview of this topic and discuss the role of advanced microscopy in battery research, development, and production. In the second part, Danielle and Kimberly will introduce Dragonfly Energy and share how this innovative battery manufacturer applies advanced production approaches. Finally, we will explore specific applications of SEM, FIPSEN, and Microscopy in characterizing dual-coated electrodes with particular attention to porosity analysis. And if you have any questions, so we'll be glad to answer them after this session. Just, for example, you can please drop them into the chat. So first, I would like to briefly introduce TESCAN. So it is globally operating company with its headquarters, main R&D, and production facilities based in Brno, in the Czech Republic. We develop and manufacture a broad range of microscopy solutions, from scanning electron microscopes to focused ion-beam SEM systems, 4D scanning transmission electron microscopy instruments, ultra-high vacuum platforms, micro-CT systems, and most recently, laser-based solutions. In addition, we specialize in customized and application-specific systems tailored to the needs of advanced research and industry applications. With its microscopy solutions, TESCAN focuses on 5 key application areas: material science, semiconductors, batteries, life sciences, and geoscience, aiming not only to deliver instruments, but also complete analytical workflows addressing specific research and industrial challenges. And now let's take a closer look at lithium-ion batteries, what's behind them and the current challenges in their research, development, and production. So what's inside a conventional lithium-ion battery? So it's a complex system composed of various materials, components, and chemistries, from active material particles to current collectors, separator, electrolyte, and casing. And to enable proper battery manufacturing and innovation, it's essential to understand its composition and internal processes, from the millimeter scale down to the nanoscale. So this challenging task requires multiple analytical techniques to achieve a comprehensive understanding of material properties. Among these, analytical workflows based on electron microscopy and X-ray microtomography are key to acquire multi-scale structural and compositional information with high precision. And these workflows help to address the main challenges in battery research, development, and manufacturing. Enhancing safety is a top priority. It's key to improving overall battery stability and preventing thermal runaway, which can lead to even catastrophic failure. Extending battery lifespan remains a major challenge. The goal is to increase the number of charge cycles so batteries last longer and stay reliable. Research also focuses on enhancing capacity, both gravimetric and volumetric, to meet the growing energy demands of electric vehicles and large-scale storage. Improving charging efficiency based on finding the right balance between the fast charging and maintaining battery health is another goal. And to address the previous challenges, it is necessary to innovate battery technology, apply new materials and architectures that aim to achieve the best combination of sustainability, performance, and cost. Finally, streamlining production is important as well because greater efficiency reduces costs and lowers the environmental impact of the manufacturing. And together, these efforts drive the development of safer, longer lasting, and more efficient battery technologies for the future. So let's see how advanced electron microscopy and X-ray microtomography contribute to battery production and innovation. As mentioned earlier, the lithium-ion battery is composed of various components and materials ranging in size from the nanoscale to the millimeter scale. And following the manufacturing process, it's essential to use imaging and analytical methods that can characterize everything from active material particles to the electrode level, and even the entire cell after assembly and cycling. To tackle this multi-scale challenge, we can combine ultra-high resolution electron microscopy with non-destructive micro-CT imaging. So how can these analytical methods be applied in practice? So ultra-high resolution scanning electron microscopy is a powerful tool for ensuring the quality of produced battery cells. It's highly effective for examining the particle properties of active materials, including morphology, size distribution, and surface texture. It also enables the study of separator porosity, electrode material distribution in surface and cross-sectional views, and the detection of contaminants originating from raw materials or production processes. In failure analysis laboratories, electron microscopy is essential for identifying local particle degradation and electrode damage, such as cracking and delamination. With the FIPSEM instrument, it is possible not only to prepare large cross-sections across the full electrode thickness by FIB milling for subsequent subsurface observation, but also to perform large-scale FIPSEM tomography, so to study the 3D distribution of battery materials. And when integrated with time-of-flight secondary ion mass spectrometry, TOFSIM, so tomography provides not only structural, but also chemical information. And this enables, for instance, highly sensitive analysis of lithium distribution in cycled electrodes to reveal the layer relationship between the chemical composition and electrode degradation, to localize trapped lithium, and to study distribution of composition of the solid electrolyte interface. Cycled battery materials are typically highly sensitive to air and moisture. Safe handling and prevention of sample degradation during transfer between the glove box and the microscope are ensured by using an inner gas transfer system. And within the microscope, cryogenic conditions can also be applied to minimize damage to ion beam sensitive samples and to reduce material deposition during FIB milling. So for these reasons, FIPSEM is essential for the comprehensive characterization of battery materials in R&D, quality assurance, and failure analysis laboratories. When studying the quality of assembled cells, micro-CT is extremely valuable because it enables non-destructive imaging of all internal components. This technique helps ensure battery safety by analyzing anode overhang, identifying contaminations, and it also supports performance evaluations through the study of the electrode porosity and material distribution. In failure analysis laboratories, microSET is used to investigate battery damage such as electrode delamination and cracking, and moreover, it allows in situ studies of internal battery processes during cycling and under specific environmental conditions. So advanced electron microscopy and X-ray microtomography from TESCAN can support every stage of the battery value chain. If you would like to learn more about how these solutions can and analytical workflows can contribute, just please visit TESCAN's battery-related web pages. And the link and corresponding QR code will be provided at the end of this session. And now, in the following minutes, Danielle and Kimberly will present a specific example of how these microscopy solutions can be applied to drive innovation in battery technology.
Thank you, Tomas. Like Tomas said, I'm Danielle DeCapito, and I'm part of the Dragonfly Energy Research and Development team. I specialize in characterization. And today I'll be giving a brief overview of Dragonfly Energy, so who we are, what we do, and how our R&D efforts are currently shaping the future of battery manufacturing, both at large scale and in the lab. So, as of October 2022, Dragonfly Energy is a publicly traded company on NASDAQ under the ticker symbol DFI. Because of this, I am now required to present these legal disclaimers at the beginning of all presentations. So, Dragonfly Energy is headquartered in Reno, Nevada, and we are a leading manufacturer of high-quality lithium-ion battery packs, delivering energy storage solutions across multiple sectors. Our non-toxic, deep-cycle lithium-ion batteries are currently replacing traditional lead-acid batteries in RVs, marine vessels, off-grid systems, and other energy storage applications. Our core business, lithium-ion battery pack manufacturing, is what fuels our innovation and supports the research and development that is transforming our industry. A key focus of these research and development efforts is achieving full vertical integration and onshore lithium-ion battery production. Currently, we import our cells from an overseas partner and integrate them into our custom pack designs. But with our proprietary dry electrode manufacturing process, we're paving the way for a fully domestic cell production future, completely eliminating the need for these imports and creating a US-based supply chain. We have over 90 patents filed and pending at Dragonfly Energy, covering our dry electrode process, next-generation technologies like solid-state batteries, and our advanced pack designs. At Dragonfly Energy, sustainability and innovation are at the heart of what we do. One of our primary goals is to establish a closed-loop production approach, reinforcing our leadership in sustainable energy storage solutions. Now we'll jump into research, innovation, and production at Dragonfly Energy. We are more than just a battery manufacturer. We focus on delivering end-to-end storage solutions that go beyond just the battery pack itself, and truly innovation drives everything we do. Our expertise spans cell manufacturing, pack design, large-scale assembly, and system integration, enabling us to deliver tailored solutions for OEMs across a wide range of industries. By maintaining a closed-loop ecosystem, we're able to connect every stage of development, ensuring optimized performance, efficiency, and sustainability. From our smart battery features and advanced pack designs to our proven record of quality and support, we're committed to delivering industry-leading solutions. And with American-based design and assembly, a state-of-the-art production facility, and a growing presence across multiple sectors, we continue to evolve and expand. On the research and development front, which I can always talk more about, we're pushing the boundaries of our next-generation lithium-ion chemistries with PFAS-free and non-flammable cells, and advancing intelligent battery communication through our platform, Dragonfly Intelligence. Our ability to engineer complete system solutions for large OEMs allows us to boost efficiency and tailor innovations to our specific customer needs. And at the core of our manufacturing process is our patented dry electrode technology, a chemistry-agnostic, space-saving, and energy-efficient method for scalable, cost-effective battery production. And by combining cutting-edge equipment with deep technical expertise, we're shaping the future of energy storage and reinforcing our role as an industry leader. The battery industry has only recently started turning its attention to dry processing as the next major innovation in lithium-ion manufacturing. But at Dragonfly Energy, we have been advancing this method for over a decade now. To us, the advantages were clear with its proven sustainability and cost effectiveness. But how does our process compare to the industry standard process? So the scenario specifically that we're going to compare is that of slurry casted cathodes. So as many of you may know, traditional electrode manufacturing, specifically with cathodes, relies on toxic NMP solvent to prepare it. A slurry is created, which is just the solvent in the active material. It's poured onto a current collector where it then spreads out and dries. And because of NMP's toxicity and high boiling point, the drying process often requires ovens that are up to a quarter-mile long, and this just consumes vast amounts of energy required to bake off any residual solvent and then to recondense it into a closed-loop system. Dragonfly Energy's process completely eliminates these steps by using two off-the-shelf solutions, a feedstock preparation step and a dry coating step. After these substitutions, however, our electrode is processed exactly the same way as it would be in a traditional electrode and cell assembly line. So we use spray drying to prepare our feedstock material, which is just our active material particles pre-coated with a polymer binder and conductive carbon additive. Spray drying is a well-established technique. You'll see it used in industries like powdered milk production. Its key advantages are its scalability, as well as its ability to create thin, uniform coatings. And by implementing spray drying, we're able to achieve excellent material dispersion and good homogeneity of these powders. Our second technique implemented is powder coating. This is also known as electrostatic deposition, and it's widely used in the automotive industry to paint car parts. This method's scalability and chemistry-agnostic nature lends itself to efficiency and versatility, which is highly desirable for our process. So to tie it all together, Dragonfly Energy's proprietary dry electrode process offers clear advantages over the traditional manufacturing process. It's fully chemistry-agnostic. We see a reduction in its CO2 footprint. It requires less energy, and it requires much less space, lowering both upfront and long-term capital expenditures. A third-party evaluation conducted by Sphere Energy actually found that our patented process achieves over a 70% reduction in energy consumption compared to the traditional methods. By pioneering this technology, Dragonfly Energy continues to lead the industry towards a more efficient and sustainable production future. At the lab scale, our approach places R&D at the core of this manufacturing process. So we start by defining the optimal parameters for generating our dry electrodes. Once powders are prepared, our team then conducts compositional analysis, covering both routine quality control and deeper investigations into material composition. This analysis is performed at multiple stages throughout the process flow, allowing us to track losses, deviations, and compositional changes. We then correlate these findings with incoming raw materials to identify root causes of variation. And by pairing compositional analysis with our process parameter tracking, we continually refine our operating conditions and identify ideal materials for our electrode production. Once powders are validated, they're processed into our electrodes, and this is where failure diagnostics can truly begin. We analyze our electrodes from initial formation all the way through in operando testing and post-mortem studies. This full cycle approach, spanning generation, operation, and end of life, allows us to correlate processing decisions with real-world performance outcomes. And ultimately, this cyclic approach gives us a comprehensive understanding of how our materials and how our process parameters interact. On screen, you'll see just a few of the instruments we use throughout this process. Most notably, I'd like to point out TESCAN's Unitom HR system. the VegaSem and the Amber X system from TESCAN as well. Kim, I'll pass it over to her, and she'll now dive deeper into just one of the ways we leverage these tools to analyze, refine, and advance our manufacturing methods.
Thank you, Danielle, for the introduction. Hi, everybody. My name is Kimberly Ortega. I'm also part of the Research and Development Department at Dragonfly Energy, and I specialize in image analysis. So today I'll be walking you through how we used a variety of imaging techniques to evaluate the porosity of our dual-coated lithium-ion battery electrodes. These imaging methods, combined with 3D reconstruction and machine learning-based segmentation, allow us to analyze porosity in depth. So porosity plays a critical role in electrode performance. It affects electrolyte infiltration, ion transport, charge and discharge rates, and active material utilization. However, porosity should be carefully balanced, as excessive porosity can compromise mechanical integrity, increase internal resistance, and accelerate unwanted side reactions. We can typically classify porosity in two main ways, one of them being internal versus external porosity. So internal pores are within a particle, like you can see in the top left circled green circle, and external pores are between particles, as seen in the bottom right circled area. Another way we can classify porosity is as accessible versus inaccessible, which refers to whether electrolyte can reach the pores. So in the top left circled area is an example of an inaccessible pore, as there are no pathways for electrolyte infiltration. And on the bottom right circled area is an example of an accessible pore, since there are gaps between the particles where electrolyte can seep through. And for reference, the ideal total porosity ranges are typically between 20 to 30% for anodes and 25 to 35% for cathodes. Our goal today is to share how we've quantified internal, external, and total porosity using 3D image reconstruction and machine learning segmentation across multiple imaging platforms. So we began our analysis with 2D cross-sectional SEM imaging to get a quick and accessible overview of the pore structure. We applied advanced image processing and machine learning techniques, such as segmentation, which is the process of labeling different regions of an image into classes based on the characteristics. In this case, you can see that we've classified each pixel in the image into 4 classes, which are internal pores, external pores, active material, and current collector. Then a neural network was trained by manually labeling these regions of interest and teaching the model what each class looks like. Once trained, the model can then be applied to the entire dataset and automatically label every single image slice with these 4 classes. This process is very beneficial as it reduces the amount of manual time and effort required for image analysis, especially for really large datasets. So from this segmentation model, we calculated that the internal porosity was about 6.65% and the external porosity was about 15.20%. And in terms of the imaging technique, cross-section imaging is useful for rapid assessments and overviews of the microstructural differences in electrodes, but it does have some key limitations. First of all, it's a 2D dataset, so we can't access accessibility or tortuosity. And the sample area is small, which lowers our statistical confidence. It's also difficult to accurately distinguish internal versus external pores, especially where particles are clustered together, which leaves room for labeling errors. Additionally, this method introduces some sample preparation artifacts that can skew our porosity results. In this image, you can see delamination on both sides of the current collector. This is likely caused by the physical cutting of the electrode, which then inaccurately increases the measured external porosity. So without 3D validation, we might misinterpret these artifacts as real structural defects in the electrode, and while cross-sections are fast and informative, they're best when paired with 3D methods. So because of that, we moved to 3D tomography using the TESCAN FibSem Amber X. This method uses slicing and imaging to build a volumetric dataset of the electrode microstructure. So compared to the cross-section, it's a more time-intensive process, but the semi-automated workflow makes it more manageable. It also gives us statistically meaningful data and more accurate internal versus external porosity classification. Most importantly, we no longer see delamination at the current collector, So this confirms our earlier assumption that it was a sample preparation artifact and not an electrode defect. In this dataset, we also compared the upper and lower regions of the electrode and found similar porosity values on both sides, which suggests good coating uniformity. Additionally, the total porosity measured from this 3D analysis falls within the ideal range for cathodes, which was between 25 and 35%. Our next step is to enhance the segmentation model to include accessible versus inaccessible pores and to explore tortuosity to better understand electrode transport pathways. So here's a video of the full 3D tomography dataset with its segmentation model that differentiates internal versus external pores. This visualization helps interpret the microstructure a little bit better, as you can see how pores are distributed and connected, which is something that's simply not possible with 2D slices. This is a really meaningful tool for both qualitative and quantitative insights. We also looked at X-ray micro-CT data using the Unitom HR system. This technique is non-destructive and it's ideal for capturing larger volumes, which makes it well suited for bulk analysis. For this imaging technique, we focused on total porosity, which was calculated at 8.16%. So it's currently not as accurate as our other methods are, and the internal and external pores were not classified as they were not clearly distinguishable at this resolution. So although micro-CT can't yet capture pore accessibility or tortuosity at this scale, it's still a valuable insight for evaluating uniformity, large area defects, and performing non-destructive quality checks. So here's a video of the complete micro-CT dataset, which provides a macro scale view of the electrode structure without damaging the sample. We have many goals for advancing this work using micro-CT, so here are some of the areas of interest. In terms of porosity, we want to enhance the segmentation model to be able to classify internal, external, accessible, and inaccessible pores. We also want to analyze active material thickness consistency on both sides of the current collector, as well as evaluate the condition of the current collector itself by checking for delamination, tears, or folds. Lastly, we want to detect defects and contamination in the material, such as foreign particles. These next steps will help us build a comprehensive understanding to support our R&D efforts. So to summarize, we presented a multimodal approach for evaluating porosity in our dual-coated lithium-ion battery electrodes by using 2D cross-sectional SEM, which gave us fast initial insights, 3D fib-SEM tomography, which eliminated preparation artifacts, and X-ray micro-CT, which was non-destructive and used for bulk analysis of total porosity. Each technique has its strengths and limitations, as we discussed, but together they offer a comprehensive picture of the electrode's microstructure. Thank you all for your time. We're very happy to participate with the Volta Foundation, and we're open to any questions or valuable insights. And if you have any questions afterwards, please feel free to reach out to us through LinkedIn.